Welcome to the Data Architecture Elevator podcast. Created by Agile Lab, we will explore the dynamic intersection of technology, innovation, and practices in the data space. Our company purpose is to elevate the data management game of companies that want to be data-driven, and this is the goal of this podcast too. For more information and insights, visit our website at www.agilelab.it and feel free to reach out our architects on LinkedIn with your question. Now let's step into the elevator with Agile Lab data architects. Welcome to this new episode of Data Architecture Elevator. Today we are with Irene.
Hi.
And Antonino.
Hi.
Okay, so recently we are working on a couple of use cases, really interesting, where basically we have a huge load of incoming data in a multimodal way. So it means audio, text, images, and also video. And this load of information need to be classified, labeled, and also enriched with further information. And we are leveraging LLM to do this, but very soon we realized that when the load of information is huge, scattered, and also you need strong performances in the inference, you immediately need to do a lot of optimization. Basically, the first thing you need to do is to remove the online models and rely on hosted models. And maybe, Antonino, you can explain why online models could become a bottleneck in such scenario.
Yeah, so basically when you have to process a huge amount of unstructured data, you need to do several API calls to your model provider. If you pay as you go or you have some API consumption that you pay, the cost becomes prohibitive when the volume becomes large. So in this case, you can instead host your own model and take advantage of the efficiency. In this case, you can select the best model for that application, so you are not forced to use the top class largest model, but already select from the get-go a smaller model that is good enough for your specific case.
Sorry, you talk about cost, but in some case, for example, with the video processing, it's also a matter of latency. You cannot keep the pace scaling on external API to classify all the video frames or stuff like that. Is it right?
Right. For video data is especially important to feed the data to the model in the most efficient way, and adding a hop through a REST API, it's not efficient at all. So in this case, you want to use some specialized pipeline to optimize that, so to reach a high throughput, of course.
Yeah, and when you move into hosted models, so it means that you are leveraging your own infrastructure to host these LLMs. Basically, you immediately become eager to optimize the consumption and the allocation of GPU. So we have seen there are several ways to optimize this kind of workloads. So the first, let's say, macro area of optimization is inference acceleration. Maybe, Irene, can you spot a couple of optimization methods?
Sure, but first thing, we should always select the smaller model useful for our purpose. So, for example, if we need to do name entity recognition, there is no need to use the last model, but we can rely on a smaller model based on BERT architecture, where we have 100 or million of parameters, whereas the last model have 100 of billions of parameters. So we have a factor of 1,000 So this is the first thing to do, of course. Then if the smaller model don't have exactly the result it should have, we can still fine-tuning it in order to optimize the parameter for our purpose. Then we can also rely on technique like distillation, where we have a big model that is teaching to a smaller model to do a specific task. This is very useful because we know that the large language model are trained on a huge amount of data, and they have knowledge, specific knowledge about so many domains, but maybe we need knowledge about a specific domain or a specific task. So we don't need so many parameters. Is completely unuseful. Then we can use also technique. The technique for fine-tuning are rising so much. Every day we see new techniques. Now we can also rely on a new technique of reinforcement learning. They use directly the output for fine-tuning the model, or that don't need human interaction for ranking the answers. So it's easier now to fine-tune our own model. And then we have the specific technique for accelerating the inference, like page attention. We can use technique as quantization, and many other.
So basically, the suggestion is if you can restrict the scope of the use case, it's completely useless to leverage general purpose weights in the LLM. So the goal is to fine-tune the models for specific purposes, so we can reduce the size of these models, and they will occupy less resources on the physical infrastructure. Also, we tested different methods about model serialization that very often are including layer and tensor fusion. Antonino, can you explain a bit this kind of technique, in which case it's possible to use this?
Yes, when you have to run inference on a model, you need a runtime, a specific runtime to execute all the computation needed by the model. And this specific runtime, it could be TensorRT LLM or VLLM, SGLang, and others. They all expose some kind of low-level CUDA functionalities, building blocks, in order to implement a specific model architecture. So normally you have to take your original model and translate it to a specific runtime, so convert it to a specific runtime. And one of the optimization that you can enable during this conversion is, as you say, the layer or tensor fusion. That is basically putting together a operation in one single CUDA function operation or core, and this speeds up the whole computation essentially, and it is a basic technique used when you deploy models.
So when you choose your physical infrastructure and you host the model in your own physical infrastructure, you have also this possibility to better align the model to the infrastructure where the inference is going to run. And also this is completely decoupled by the infrastructure that you use for training or fine-tuning. So you can train the model on a specific infrastructure and then optimize the model for the inference time that is completely disjoint phase of the model lifecycle.
Another technique that you can use for decoupling to optimize the inference and decoupling it from the training phase is quantization, where you can decrease the precision of how you save your weights. For example, you can go from 32 bits to just 8-bit, and you can do it both on the weight of the model, but also in the way you represent the activation function. And the way you decide to quantize your model depends on how you will use it for inference. If you have a big batch you want to use with big batch, it's better to quantize both the weight part and the activation part. Whereas if you just have a low batch, little batch, you can just quantize the weight part.
Yeah. So, for example, in video streaming, where you can pack a set of frames that potentially are also quite similar each other, you can create a batch of inference and send this batch and leverage this kind of optimization.
If you run your inference on batch, is already much faster than if you run one by one. But then you can add the techniques that Antonino said before, more quantization, or also other techniques like page attention. This will decrease the memory used by your model, so you will decrease the quantity of data you are moving, and this makes much faster.
So, and all these techniques are increasing the, let's say, atomic performance of the inference. So the single inference time, the latency also of the inference, but very often you have also to take care of the horizontal scaling. Maybe Antonino, what kind of techniques did we see in terms of routing and load balancing? So when you have to load balance multiple inference requests on multiple GPU, but also when you want to activate and deactivate the GPU. For example, when the incoming traffic is slowing down during the night, maybe. So when you have a high volatility in the traffic throughput. So what kind of techniques are available in the market right now?
So for this, normally on top of your runtime to execute the model, you use a server, an inference server, to wrap the runtime, and the inference server will take care of getting this request, this incoming request, and dispatching it to different models potentially. One of the most used is Triton. That is a server made by NVIDIA that has been also adapted, used for LLMs. But there is also a new tool published just a few days ago that is Dynamo, made by NVIDIA, and as Triton is another open source tool. And Dynamo is specifically optimized for LLM, large LLM. Unlike Triton, that is a general purpose model server. Being optimized for LLM allows to implement some specific routing optimization, because it's very common that you need to distribute your model across several GPUs, and so communication between GPUs is costly. You need to have a logic to share the cache and so on. So reducing as always in engineering, you reduce the scope of applicability, but you increase the of the optimization that you can do. And this is an interesting new tool. I would say these two are the most
Instead
interesting at the moment.
For the auto scaling of GPU, so switching on and off GPU server, or what is possible to leverage?
Typically, if you have a large cluster, that is on-prem, you manage it with Kubernetes, and the horizontal scaling is kind of a orthogonal problem to the optimization of a single request arriving. So in that case, the scaling can be handled by an additional layer like K-serve that will run on new nodes or new node groups, and will increase the available throughput for the whole system.
Clear. So basically, there are common challenges that have been already solved in API scaling world, like
Exactly.
Kubernetes scaling, but also API gateway and API load balancer and so on. Then behind this general purpose layer, there are very specific optimization techniques for LLM that you can put in place. Okay, thank you so much for this deep dive on LLM optimization techniques for inference, and see you to the next episode.
See you.
Bye bye.
Thank you. Bye.